Today we're having a look at lecture number 11, and that's to do with arches. Arches can be defined as curved structural members, and that's those old as the hills. The Romans were building arched bridges in Europe 2,500 years ago, and all over the world you can find arches that have been built by people many years before, centuries before engineering even became a science. So it was just a basic form that actually works very well in supporting things. But arches can be defined as curved structural members. They're usually found today in structural elements employed as main roof members, sports arenas, shopping centres and pavilions. Arch forms are also found in tunnels, and if any of you have driven around the tunnels around Brisbane, you'll know what I mean. Those are arches. Those precast concrete sections that have been put in there are actually arches. A broad definition of an arch is a curved element whose supports are either fixed or pinned. Now this is a fixed arch there, which means you've got complete fixity at this point, and the arch cannot rotate there. And this is a pinned arch. Now both of these are very difficult to analyze mathematically, and you have pages of calculus analyzing those. Fortunately today with software you'll be able to analyze them as quickly as you could analyze a three-pinned arch on software, but we are going to stick to three-pinned arches, which are statically determinate, not redundant structures, and that's what we're going to be doing today. Now, I'll jump straight into an example. A three pins, 1, 2, 3, it means that that's a stiff member there, a stiff member and a curve there, but they can actually rotate around those pins. Not move anywhere, but rotate around them. A three-pin semicircular arch of 7 meters radius is shown in the figure. Find A, the horizontal thrusts and vertical reactions at A, B, and C. So we're looking, that's a horizontal thrust, which we would call HA. And this would be a vertical reaction, VA. And the same thing for VC and HC. And in doing that, so that you obey the laws of equilibrium, you would end up with two forces acting there on that pin there, and also over there, for this whole system to be in equilibrium. So we've got to find these, which is a very simple method, as you will see. We have to work out what the bending moment in this element is at point D where the load is, and we have to work out what the radial thrust and shear is at that point. And if you looked at this and you had this curve like this, the radial thrust is the force that ends up acting in the element at that particular point. That's the thrust. The shear is the shear force tending to shear through the material over there. So we'll be looking at all of that today. So let's get on to the solution of that one. To find the vertical reactions, which are VA and VC, we take moments about A. Take moments about A of everything to the right-hand side of A. So 5 times 11, because this thing's radius is 7 meters, and let's just put these dimensions in here so we don't get lost. The radius is 7 meters. And this dimension was 3 meters. If that dimension is 3 meters, then this dimension here would be 11 meters, wouldn't it? 11 meters. I'm sitting in an uncomfortable position here. I should move that around a bit. Yeah, that's better. I'll just check that out. Yep, that's right. So what we've got is we take clockwise and anti-clockwise moments just as you would if you were analyzing a beam. So don't be frightened by the fact that the things are curved. Really, they're not that difficult. And you will be getting an arch in your assignment anyway, which I'll be sending to you next weekend. a bit more complicated than the one we're looking at, but I'm sure you'll cope. So we're taking moments around A. Clockwise, we have 5 times this horizontal distance, 11 meters. 5 times 11, that force there. We have VC times 14 meters, because the diameter of this thing is 14 meters going the other way. So you could have written 5 by 11 minus 14 VC, but it's already been moved to the right where it becomes a plus. When you solve that equation, you get VC equal to 3.93 kilonewtons. So VC is 3.93 kilonewtons. Now we take moments around C to find VA. We're ignoring the horizontal forces at this moment, and we can because they're passing right through the points that we're taking moments about, so they'd have no lever arms, so they wouldn't be anything. So we're going to take moments about C now, which is there. We have 14 VA, VA times 14 meters going clockwise, positive, equals going anti-clockwise 5 times 3. 5 times 3 is going anti-clockwise around this point. So VA, clockwise around there. There are no other forces, 5 times 3. We solve that, we get VA equal to 1.07. We can now check for vertical equilibrium. You have a force coming down of 5 kilonewtons. These two, the sum of these two forces should equal 5 kilonewtons for this system to be in equilibrium. So if you add VC to VA, you get 5 kilonewtons. Our arithmetic is correct. Moving on, we're going to look for the horizontal components now, these two horizontal forces. And don't forget this fact, those horizontal forces always equal each other. Otherwise your arch would take off down the countryside. So remember that. HA is always going to equal HC, it has to. So to find HA and HC, take moments around B to find HA, and we can ignore everything to the right of B, like that. We're going to take moments around B of these two forces, and the only unknown is HA. So we've got 1.07 times 7 going clockwise around there, and you always measure this dimension at right angles to the point you're taking. You don't measure any other dimension. That force is acting up like that, so that's the distance. That's why that's 1.07 times 7 minus 7HA. You could write that like that, and I'll just do that just for anybody who's got any qualms about this. 1.07 times 7 minus 7 times HA equals 0. That's what I've got there, because when you take this minus 7HA at the right hand side, it becomes a plus 7HA. You solve that and you find that HA equals 1.07. Now if you were confident enough, you'd say, well then HB is also going to be 1.07 because it has to be for horizontal equilibrium. But we're going to do it the long way. We're going to take moments about B and ignoring the left hand side of the arch. So we're going to take moments around there now. And we've got 5 times 4 going clockwise, positive. 5 kilonewtons times 4 meters, horizontal distance, plus 7HC. HC times the distance from there to there, because that's the line of the force, that's the dimension. 7HC minus or equals 3.93, which is a VC times 7. It is going anti-clockwise around B. And again, HC comes out at 1.07, exactly the same as HA. And I've made a note here, for equilibrium, HA must always equal HC on whatever geometry of arch you have. Now we going to look at the thrusts at the top, at the crown, at point B. The horizontal forces are transferred up there for this thing to be in equilibrium, 1.07, and we've got shear force on that pin, You've got 1.07 going up there, and for that to happen, you have to have 1.07 coming down. So that's that joint in equilibrium there. By inspection, the horizontal and vertical thrusts at B are shown. We now come to part B, which was find the thrust and the shear at D. There are arches with the horizontal forces and the vertical forces that we've just computed. The first thing we have to do for part B, what we have to do is we have to find the bending moment at D. We get onto the thrusts later on, but we have to find the bending moment at D. And y squared, that dimension there, equals 7 squared minus 4 squared. And how did I get that? Well, I'll just sketch it for you. If that's this circle, like this, and we have this point here that we got, what we're trying to find is this vertical dimension there, that vertical dimension. And if you drew a line down from the top of the arch, that dimension there is 4 meters, as you'll recall, because that's 3 meters, so that's 4 meters. And what we're doing is, using Pythagoras to find this vertical dimension. So on a right angle triangle, this old Greek sitting in Athens 2,500 years ago came up with the idea that for a right angle triangle, if you had 2 of the sides, you could find the other one. Now what do we have? We have 4 meters there, we have the radius of the circle, which is 7 meters, and we're looking for this dimension there. And that dimension there is what we're doing here. 7 squared minus 4 squared, the root of. So y squared equals 7 squared minus 4 squared, or y equals the square root of 7 squared minus 4 squared, 5.74 meters is that dimension there. How do we find the bending moment at this point? We ignore everything to the left of that point, and we take moments around D. So MD, 1.07 times this dimension we've just found. It's going clockwise around there at a distance of 5.74 meters away, minus this force times 3, because it is 3 meters away. And as I said, you measure all these dimensions at right angles to their lines of force. So that's the line of force there. It's 3 meters. So that force there acts 3 meters away from there. This force here acts 5.74. So we take moments around D of everything to the right of D. 1.07 times 5.74 is going clockwise around D, minus 3.93 times 3 anti-clockwise, and we're left with a negative bending moment of minus 5.65 kilonewton meters. And that's a bending moment at D. I'm sure you'll all agree with me thus far, it's not that difficult. So the next issue is to work out what the thrust and the shear is at this load point where the 5 kilonewton load is. I'd done this previously by calculus, but it's a pure geometric thing using Euclidean geometry. And I'm only trying to impress you guys with my knowledge of the old Greek philosophers. Euclid was a fellow that practiced geometry, and he was very good at it. And at one time, you studied Euclidean geometry at high school under that very title, EUCLID. But I've done this one by calculus. A later one I've done in the tutorial today. I'll show you how you just do it by plain geometry. So these are the conditions here. And what we've got to do is find the slope of the tangent to the circle at that point. And I've done it by just writing down the equation of the circle, which is r squared equals x squared plus y squared. Now some of you doing maths too would have come across that. Rearranging that, y equals the root of r squared minus x squared. You differentiate that and you will find the slope in radians, and you can actually then convert that and find that it's at 35 degrees. Now the 35 degrees that we're looking at is the 35 degrees there, because that slope of the tangent to the circle at that point is at 35 degrees to the horizontal. There it is. As I said, we'll do it with geometry later on. Now, we then look at the force components of those loads. And I'll just try and combine these two if I can get them on the same page. I think I might be able to, yeah? Yep. We'll do the force component of the 1.07 kilonewton load, which is this reaction, in fact. We take it up there, 1.07, and you could even do this graphically if you wanted to, because it's a right angle triangle. So we've got 1.07 kilonewtons moving from right to left, and there the arrow is. Our thrust is 0.87, because using trigonometry, cos and sine, which I've done over here, okay? N is the thrust, that's the symbol we use for thrust, and S is the shear, which is the shear force tending to shear through this member that way. Thrust is the compressive force in the arch. You do it by using a right angle triangle. 1.07, this is at 35 degrees, your line of thrust. At this point, you drop a line down perpendicular to your thrust, and this gives you your shear. It's going down, so it is a minus quantity. Your shear at that point, due to the horizontal thrust from the support, is minus 0.61 kilonewtons. So that's the force component of the 1.07 kilonewton HC, horizontal force. We now look at the force components of, let me move this up. We now look at the force components of the 3.93 kilonewton load, and there it is there, the 3.93 kilonewton load. We've drawn it in there. That's this vertical reaction down here. And again, there's the 3.93 going up. There is the shear force at right angles to the tangent of the circle. And this is the thrust. Now, when you sum these algebraically, taking account of the pluses and minuses, you end up with a thrust at D. A thrust at D of 3.12, that means the force, the compressive force in the arch there is 3.12 kilonewtons. Your radial shear, by the time you've done your arithmetic, is 2.61 kilonewtons, shearing across the member there. And that's it. That sort of wraps that up. It's not rocket science, as they say. And as I said, for those who have have a bit of trepidation about the calculus, don't worry about it. I'll be showing you how to do it using pure geometry. You won't need to do that. Okay, so let's move on. So we've got a 3-pin semicircular arch of 6-meter radius as shown in the figure. Calculate the horizontal thrusts and vertical reactions at A, B, and C. A, B, and C. In this particular one, we have a uniformly distributed load acting horizontally like that. And I mean, it could be earth that was actually resting on a tunnel roof, if you wanted to, but we're taking it as 6 kilonewtons per linear meter. We asked to find the HA and VA, HC and VC, which are the reactions, the bending moment on the other side away from the load, and the thrust and shear at the same place. I would suggest you, the students listening to this lecture, get familiar with this operation, because it will benefit them in the next few weeks, that I can assure you. And if that's not a hint, I don't know what is a hint. So, moving on to the solution. Moving on to the solution of this arch, we're going to find the vertical reactions. We're going to take moments about A to find VC, taking moments around A to find VC. And we've got 6 kilonewtons per meter times 3 meters, because that's the radius of the circular arch. 6 times 3 times 1.5. And 1.5 is the distance from there to there, because that is 3, so that load acts through its center of gravity, and that is 3 meters away from VA, and that's where that 1.5 meters comes from. Sorry, my mistake, 1.5 meters, half of 3, 1.5, half of 3. Equals VC, 6 VC, or minus VC times 6, all equal to 0, but I've taken the VC across there already. Solving that, you get the vertical component at 4.5 kilonewtons, and at this stage, I'd be looking at it if I was doing this problem myself, and I'd say, what's the total load? I'd say, well, it's 6 times 3 is 18 kilonewtons, and I would guess that this VC must be a lot smaller than what VA is going to be, so I'm probably on the right track. And what I've done is, in this one case, I've been lazy. I haven't gone and taken moments around C to find VA, which you can do. All I've said is the total load is 6 times 3 is 18, and please don't do it this way. This is the lazy man's way. 6 times 3 is 18. 18 minus 4.5 is 13.5. So I've said, right, this here is 4.5 kilonewtons. This is 13.5 kilonewtons. And just by now, you intuitively, because of your because you people have done many problems in statics, you know that the load on the vertical load on this side is going to be a lot bigger than it is on that side, because this load tends to rest on that more than it does there. So there we have it. Now we're going to find HA and HC. We're going to take moments around around B to find that. So we've got 13.5 times 3 going clockwise around B, positive, 13.5 times 3. Must equal or minus, it's the same thing, because you can then take it across the other side. Must equal 6 times 3 times 1.5, which is 6 times 3 kilonewtons per meter. 18 kilonewtons times the distance from there to B, 1.5 meters. Plus 3 times HA, because HA is acting there, like that, around B, and the dimension from there to there is 3. So HA times 3. When you solve for HA, you get 4.5 kilonewtons. So HC then, doing it the lazy way, would be 3HC if you took moments around this point, around B now, sort of ignoring everything to the right. We've got 3HC at 3 meters, HC going clockwise around B, because that's what we're doing here, taking moments to find HC. 3 times HC must equal or minus 4.5 times 3. 4.5 is acting up there, also 3 meters away. If we solve that, 4.5 kilonewtons. We know we're right. We have horizontal equilibrium, HA equals HC. So no problem. Okay. I would advise you guys to do these problems again yourselves without trying not to look at your workbook, to see if you remember what the method is once you've had a look, gone through this lecture. At the pin, the vertical reactions are 4.5 there. And the bending moment at X is calculated the same way as the first one was. We've got 3 meters, which is the radius, minus 2 meters, which is this dimension there. Root of 3 squared minus 2 squared gives you this vertical dimension. And you can see that on the first problem I did in detail. I'm sure you're all senior students now, and I don't have to labor every little point. So y is this dimension, and I've shown you how to do it in the first problem. Works out to be 2.23 meters in this particular case. So the bending moment at X then, bending moment at X, if we take moments around X, is 4.5 times 2.23, which is the distance from there to there, worked out by Pythagoras, minus 4.5 times 1 meter, going the other way, okay, anti-clockwise. Gives you a bending moment of 5.53 kilonewton meters at X. That answers part B of this question. Part C, I've done using, let me just erase this at this stage. Part C, I've done using the calculus again to find the actual angle of the tangent to the curve at that point. It works out at 42 degrees. As I said, don't stress over this. I'll be showing you on a more complicated problem in the tutorial how you can actually find that in a much easier fashion for those who find that a bit difficult. So the angle is 42 degrees, and we look at the force component of HC now. That's a 4.5 kilonewton load, that one there. 42 degrees is the angle of the tangent. That N is the thrust, as I said to you. That's 4.5. You can construct this triangle knowing that this has to be 90 degrees. And from that you will find out what that length is. You could just use trigonometry. I mean, the cosine of 42 degrees is N over 4.5. There you are. Cosine of 42 is N over 4.5, gives you N. The sine of 42 will give you S. It's going down, it's a minus when it's going down. Minus 3.01 kilonewtons. And these are the force components of the vertical force of 3.93, which is VB, done in exactly the same way. We note that angle is 35 degrees, 55 degrees. There the trigonometry is. Very straightforward. And when you add up the force components of the 3.93 kilonewton load and the horizontal force as well, so in other words, that we can find the thrust at X, you come up with this answer, 6.34. And I would suggest before you throw your hands up in horror that you actually study this, that you get a piece of paper and sketch this out. We're doing online learning. You need to actually do quite a bit of work yourselves. Sketch this out and try and understand it yourself. It's no use just asking somebody to help you. You'll find as you travel through life, and I can assure you of this, that you have to work a lot of things out yourself. And then the final shear at X, the final shear at X there, going across there, the final shear at X is 0.33 kilonewtons. The thrust is 6.34, so the thrust in the member there, the final thrust is 6.34. Right, we're nearly at the end of this lecture, so I'll just press on with it. We've got a arch which does not have actual dimensions. It has alphabetical letters on it, but conveniently the radius of the small segment there is half the radius of the bigger segment of the circle. So we can set up some equations to solve this using R's, using HB, VB, HA and VA, and find out what HA and VA and HB and VB are. And that's what we have to do in this particular problem. You can start off by saying for equilibrium, HA must equal HB, because that's a given. In any of these arches, and I said this at the outset today, the horizontal force acting that way must be exactly the same as the horizontal force acting that way. Otherwise, you have a problem and this arch is going to travel across the countryside. So for it to stay in this place, they must equal each other. And so you can write them down like that. You can then simplify them by saying that HA equals HB equals H. You don't have to write the A's and the B's. So what we do, first of all, we take moments about C for the left-hand side. About C for the left-hand side, blanking off the right-hand side. And we have H times R, H times R equals VA times R. It doesn't matter which way around they are, because at the end the R's cancel out and you're left with H equals VA. So the horizontal force there equals vertical force, and you'll find that with these arches where there's no load on a particular section of the arch like that, the horizontal thrust always equals the vertical force. So we've proven that in the first case by taking moments about C. We now take moments about C for the right-hand side of the arch, covering that side up. We have H, which is HB, but H times 2R is going in a clockwise direction. It's 2R away from there, H times 2R, minus VB times 2R, because VB is going anti-clockwise around that point, and it is a dimension 2R away from the origin of the circle there, plus W times R, also going clockwise. W is R away from there. It's also going clockwise. All equals 0. So it's equal to 0 because the moment at the pin C is 0. You cannot develop a moment at a pin. We call that equation 1. We then take moments about the whole arch, about A for the whole arch. There, take moments about A for the whole arch. And we have H times R, because this H here is R away from there, and it's going in a clockwise direction around there. If you can just think about that H there is R away. So H times R is going clockwise around the pin at A. Plus W times 2R. It's also going clockwise around there, and it is R plus R away from there, 2R. Minus VB times 3R. And VB is going anti-clockwise around that point, and how far away is that line of action? It is 3R away. Minus VB times 3R equals 0, equation 2. So if we divide equation 1 and equation 2 by R, okay, throughout, okay, both sides of the equation, we eliminate R, and we're left with 2H minus 2VB plus W equals 0, and we call that equation 3. I'm sure you're with me there. If we divide this by R, we eliminate all the R's, because we're doing it to both sides of the equation, and there's 0 there, so if we divide by R, it's also, the R becomes 1 if we divide through. And equation 2, we divide the whole thing through by R, and it eliminates all the R's, which makes the thing more convenient. So we've got 2H which is this equation 3 now, is 2h minus 2vb plus w equals 0. There it is rewritten without the r's. That's equation 3, we'll call it. And equation 4 is this one transformed. We've divided through by by r rather, and got rid of it, and we're left with h minus 3vb plus 2w equals 0. And if we multiply our new equation 3 by 3 over 2, we turn it into this format there. And we call that equation 5. And if we subtract equation 4 from equation 5, these are plain simultaneous equations which you shouldn't have much problem with. If you subtract equation 4 from equation 5, 5 minus 4, this is what we're left with. 2h plus minus w over 2 equals 0. And from that, h equals w over 4. When you transpose this equation, h equals w over 4. So what are we saying? We're saying that h and this h over here are both equal to a quarter of the load. Therefore, VA must equal W over 4, because H equaled VA. We did that in the first place over here. H equaled VA. So if H equals W over 4, then VA is going to equal W over 4. There we have it. And VB is the balance of the load. This load there, if you've got a load of W over 4 the vertical reaction there, this is going to be 3/4 of W. And there it is. We take 1/4 of W away from W and we're left with 3/4 of W. QED. I can't quite remember what that Latin is, but quattro et demonstratum. I think I'm just trying to impress you guys, but thanks very much for listening to me today.